are going to go over the symmetry of graphs, including even and odd functions, and how to determine which is which. So, we can have x-axis symmetry. And in order to determine whether something is symmetric with respect to the x-axis, what we can algebraically do is replace y with negative y and determine if the result is equivalent. If we want to determine if we have y-axis symmetry, which is an even function, we can replace x with negative x and determine if the result is equivalent. And if we want to determine whether or not we have origin symmetry, which would be an odd function, we could replace x and y with negative x and negative y and determine if the result is equivalent. It helps a lot with these to see the examples. Okay. So, example 1, it says determine whether it is symmetric about the x-axis, the y-axis, or the origin. Now, we'll start with the x-axis. We'll flash back. For the x-axis, we are replacing y with negative y. Okay, so let's do that. Alright, if I come here and I replace y with negative y, so we're determining if it's symmetric with respect to the x-axis, where we're replacing y with negative y. Okay, so if I do that, I go x plus negative y squared equals 3. We want to determine if by replacing that y with a negative y, if we can still come out with the equivalent expression, or basically the same expression. So let's simplify this. If we simplify this, the x can't be simplified, I'll leave it alone. But negative y squared, negative 1 squared is positive 1, so it essentially simplifies back down to the original. Because it simplifies back down to the original, we say it is reflective with respect to the x-axis. Alright, so we've checked. It is symmetric with respect to the x-axis. Now, it can be all three, so we need to check all three. So we're going to go back here and we're going to check y-axis symmetry. We're going to check and see if it's an even function by replacing x with negative x. Okay, so we're going to check for y-axis symmetry. We're going to replace x with negative x. Alright, let's try this. So this would be negative x plus y squared equals 3. Now, does that create an equivalent expression to the original? It does not, and it cannot be simplified so that it is the original. So for the x-axis symmetry, it was able to be simplified back down to the original. But in this case, when we tried to see if it was symmetric with respect to the y-axis, we got something where that negative doesn't just go away, or it doesn't simplify down and away. So it is not reflective with respect to the y-axis. That is a no on that form. So let's check the origin. See if it's reflective with respect to the origin. Now for the origin, you have to replace x with negative x and y with negative y and see if it simplifies back down to the original. So here it would be negative x plus negative y squared equals 3. Now the negative x does not simplify, but the negative on the y here does, because negative 1 squared is positive 1, so negative y squared is positive y squared. Okay, but this does not simplify back down to the original. Because it doesn't simplify back down to the original, it does not symmetric with respect to the x-axis. So it was with respect to the x-axis, it wasn't with the y-axis, it wasn't with the origin. Okay, that's how we check. Let's do another one. Okay, and like I said, it's kind of easy to remember here, so you're kind of doing the opposite here. X-axis, you want to switch y's. Y-axis, you want to switch x's. Origin, you want to switch both. Alright, so in this one, it's y equals x to the third plus 8x. So we'll start to check if it's reflective with respect to the x-axis. So I'm going to plug in a negative y and see if it'll simplify back down to the original. Now here I could divide both sides by negative 1, but that would give me a y equals negative x to the third minus 8x. That does not simplify back down to the original, so it's not symmetric with respect to the x-axis. Let's check the y-axis. Now we can do it with the x's. I'm going to plug in a negative x for my x's. And I can simplify a little bit, but negative, that negative out here, if you cube it, it stays negative, so it really just looks like this. And you can bring that negative to the front there, but it does not reduce down to the original. So it's not symmetric with respect to the y-axis. Let's check the origin. Now it could turn out that it's not any of the three. It could be either one of the threes, it could be all three, or it could be none of them. Okay, it could be several different combinations. But let's try this. Now we're going to input negative y's and negative x's. Okay, now this is going to give us negative y equals negative x to the third minus 8x. And if I divide by negative 1 on both sides, I think this one's going to work out. The negative on the x third goes away. The negative on the 8x goes away. And we wind up with the original. So in this case, we are symmetric with respect to the origin. So symmetric about the origin. Fair enough. Alright, now let's determine whether we're symmetric about the x-axis, y-axis, or the origin. Here I have y squared equals x squared minus 8. Okay, so we'll start with the x-axis. I'm going to replace y with negative y. So I get negative y squared equals x squared minus 8. Okay, well negative 1 squared is positive 1, so this looks like it simplifies down to y squared equals x squared minus 8, which is the original. So hey, we are symmetric about the x-axis. Let's try the y-axis. Alright, for the y-axis we're going to want to replace x with negative x and simplify. Negative x squared does simplify down to x squared. So I'm looking at there does need to be a squared there. Looking at y squared equals x squared minus 8. So it does simplify back down to the original, so it's symmetric with respect to the y-axis also. Alright. Well, how about the origin? I need to do both. Negative y squared equals negative x squared minus 8. That means that y squared equals x squared minus 8. Squaring those negatives make them go away, and it simplifies back down to the original. So in example 3, it is symmetric about the x-axis, the y-axis, and the origin. So it's symmetric about all three. Like I said, it could be a combination of several of them. It can be none of them. It could be one of them. Or it could be all three. So in this case, it was all three. Alright. This one says determine whether it's symmetric about the y-axis or the origin. Okay. For checking the y-axis, then we're going to let x be negative x. Okay, that means that this is negative xy equals 1. If I tried to simplify it down, it would be xy equals negative 1. That's not the original, so y-axis doesn't work. Nope. How about the origin? On the origin, I need to replace both, so it's going to look like negative x times negative y equals 1. Negative and a negative multiplied give me a positive, so this should simplify down to xy equals 1. That's the original. So it looks like this one's symmetric about the origin. If you did want to check, it didn't ask us to check the x-axis, but if you wanted to check the x-axis here, you could. You would replace y with negative y. So it's just a regular x, it's not a negative x. And you would see that it isn't reflective about the x-axis either. So this one's only reflective or symmetric about the origin. Alright, let's look at even and odd functions. An even function is a function that satisfies the condition that f of x equals f of x equals f of negative x for all x in its domain, meaning the graph is symmetric with respect to the y-axis. So y-axis symmetry means it's even. Odd functions, definition for an odd function is a function is odd if it satisfies the condition f of negative x equals negative f of x for all x in its domain, meaning this graph is symmetric with respect to the origin. So, for a function to be even, it needs to be symmetric with respect to the y-axis, and if a function, for a function to be considered an odd function, it needs to be symmetric with respect to the origin. Okay, and we know both of those checks already. So it says determine if the given function is even. If the function is not even, then determine if the function is odd. It's going to be our approach. Okay, so it's determining whether it is even, odd, or neither. Here we have f of x equals the absolute value of x plus 3. So we're going to determine if it's even. Well, even is the same as y-axis symmetry. So I'm going to replace x with negative x. Okay. If I put a negative x in here, f of negative x equals the absolute value of negative x plus 3. Well, we know the absolute value is going to turn anything positive, so technically it simplifies itself down to the absolute value of x plus 3, which is the original, which therefore means it is symmetric with respect to the y-axis, which therefore means it is even. Because in this case, f of negative x does indeed equal f of x. If you go back to your definition here, f of x equals f of negative x is our definition for an even function. Okay, so this one is even. You could check if it's odd as well, right? So in order for us to check that it was odd, we would have to make both negative, which means that we would essentially treat the f of x like a y. So here it would be negative f of negative x equals the absolute value of negative x plus 3, which means that negative f of negative x equals the absolute value of x plus 3. But we still have this negative to worry about over here that we have to bring over, which means that f of negative x equals negative absolute value of x minus 3, which is not the original. We've determined it's even, therefore it's not odd. Okay. This one says determine whether it's even, odd, or neither. Okay, well, let's start with even. Okay, now, so here's what we're going to do. We are going to replace x with negative x. Okay, and then you try to simplify. If we do that here, it's negative 2x minus 3 over x. And what we notice here is that's not the original. We can't simplify it down to the original, therefore it is not even. Let's check to see if it's odd. Now, what you can do, because I know the negative f of x part confuses people, you can replace f of x with y. So you can write it as y equals 2x plus 3 over x if you want to. That way when you go to replace both the y and the x with negative y and negative x, it's a little more straightforward. And you plug in and you're not messing around with the negative f of x up front, because that does tend to confuse people. So I just rewrote it this way, and we want to try to see after plugging the negatives in if we can make it back to the original. Okay, well, on this left hand side it kind of simplifies like it did before, but now we have this additional negative to worry about. So if we divide both sides by negative 1 here, what we actually see is this does turn back into y equals positive 2 plus 3 over x. I drew a terrible 3, which is the original that we started with, right? So this one, it wasn't even. We determined that it's odd. Now, just keep in mind, just because it is even, or it isn't even, or it isn't, how do I say this correct? Just because it's not even doesn't mean it's going to be odd. It could be neither, right? But you can't be even and odd at the same time for a function, right? Which is a little confusing because you can be symmetric with respect to the x-axis, the y-axis, and the origin all at the same time, right? Which means that you could be, because even here, even lines up, if we go back to our initial definition, even means it's respect to the y-axis, right? And odd means it's respect to the origin, right? The reason you can't have those both at the same time for it being a function is because of that function definition, okay? And you can be symmetric with respect to the different axes and not be a function, but in order like for it to be symmetric with respect to the x-axis, it actually turns out not being a function. Something hard to think about there. Anyways, that's beside the point. Let's go with example 7. All right, here we have f of x equals the fourth root of x minus 3x to the third. We want to determine if it's even, odd, or neither. We'll start with even. Okay, so we are going to replace x with negative x. All right, so this is negative x here. There's a negative x there. And if I simplify, I've got fourth root of negative x plus 3x to the third. Unfortunately, it does not simplify back down to the original. Now, for the odd function, I'm going to let f of x be y, so it's just easier for me to work with. So here's what I'll be trying to get it back to when I check to see if it's odd. Okay, so for odd, I'm going to let y be negative y. I'm going to let x be negative x. You've already simplified this x part on the interior, so if you want to skip some steps in your simplification there and just use the justification you had above, that's fine. If you want to write it all out like I'm doing, that's fine as well. Now, you could divide this negative over to get y by itself, but the problem is you can't just force that negative into that root. So all you really wind up with is the negative fourth root of negative x plus 3x to the third, which is not the original. You can't force this negative inside this root to try to make it look like the original. So unfortunately, this is neither even or odd. So we're going to select the neither option. Okay. It says here, determine whether it's odd. First thing we'll check is if it's even. If you want to check if it's even here, then I'm going to replace x with negative x. So here we're looking at f of negative x. We'll see if that's equal to that original f of x function. Here I'm plugging in a negative 3, or negative x to the third, minus 3. Here's a negative x there. You can see kind of quickly here that it does not simplify back down to the original, unfortunately. So it's not even. But if you check to see if it's odd, like I said, I'm going to parlay this over here, replace the f of x with a y, so that we're checking negative y equals negative x to the third minus 3 times negative x plus 5. If you go to simplify it down, you're going to get plus 3x plus 5. If you divide by the negative 1 trying to force it back to the original state, you're going to get the positive x to the third. You're going to get the minus 3x. But the problem you're going to have here is you're going to wind up with a minus 5 and not a plus 5 like what you need. So is it odd? It's not odd. It's really neither because it's not even either. So you could either write that it's neither even or odd. And that's how you check to see if you have an odd function, an even function, and that's how you also check whether or not it's symmetric about the x-axis, the y-axis, the origin, or none of those. So I feel like that's a pretty straightforward lecture. You know your checks. You just have to take the time to do the algebra and work through them, and you can determine whether or not you're even, odd, or whether you're symmetric about the x-axis, the y-axis, or the origin. If you have any questions, reach out. Don't hesitate to ask. Other than that, I will see y'all next lecture.